Hi, this is Brandon Mills with the Indigenous Youth Data Analytics Internship. This project's question is analysis of Indigenous communities in Canada using the Community Wellbeing Index, using k-means clustering to sort them into different wellness groups or categories, and also which categories specifically they're struggling in. So the problem with the well-being score is that it flattens everything into the one number. So two communities can land on the same community well-being score for different reasons. So we're looking to identify the reasons that a given group lands at their community well-being score and what those reasons might be. So using clustering, we're going to develop those profiles based on the CWB data. So the question is whether k-means can find those balanced and unbalanced development profiles on its own, just from the income, education, housing, labor force, and the CWB final result. So these are the fields for the data set. There's one more variable that isn't mentioned by the project description, which is the population size. I began by including it just to have an additional baseline, but based on the correlation heat maps that I eventually wound up producing, it had a less than 50% correlation. Removing it also increased the, it made the final result make more sense. As it stood with population included, it identified below the mean and above the mean fairly well, but it didn't, it literally did that only based on the community well-being index, which wasn't very useful. So we prepared and explored the data. We got the data into the cluster-ready shape and standardized it. I applied k-means to find the actual groupings, and then once that happened, I used the results to identify profiles based off of those results. So loading the data, since this is a Canadian data set, I had to use the Latin 1 encoding set because there were French community names and Métis community names, as well as others that use the accent aigu from French, as well as other characters. So that had to be considered. The data set contains data for everyone in Canada, not just Indigenous communities. Since the question focuses on Indigenous communities, I filtered to Indigenous identity by including the First Nations, Inuit, and Métis communities. I checked for the missing values and the duplicate rows and dropped both. The part that actually matters is the standardization. K-means groups the points by Euclidean distance, and Euclidean distance, it matters the magnitude of the variables. So the standard scalar from scikit was applied in order to standardize all the data. So by doing that, all 5 variables are within a standard deviation that allows the model not to give a biased weight to one of the input variables. And you can see here, based on the visualization, the initial groupings of data with no categorizations. This is the correlation heat map that we discussed, and we can see the impacts on community well-being in the far right column based on the data in the left. So housing has by far the greatest impact on community well-being, with labor force activity actually having the least, which I thought was interesting. Although it does make sense to me that income is more important than labor force activity. So before trusting the results, we look at this data. Summary statistics and the box plots told me about the spread and the outliers. There weren't very many outliers once we filtered for the Indigenous community. Before we did that, there were obviously a large number of outliers because of the larger data set. This is the piece I leaned on the most because it's what allows me the greatest view into what the model is actually thinking about these input variables. So for choosing K, I thought about just doing what we did in class and trying to vibe it out. But I remembered that we discussed elbow clustering, so I looked it up and I found Yellowbrick, which is an extension of the scikit module rather. So I used the k-elbow visualizer, which produced the graph you see on the right, so that I didn't just arbitrarily choose. It tests the k values from 1 to 15, which is an arbitrary upper limit, but you can see that it measures the distortion, which is unexplained variance, to find optimal fit at k. So as k increases, distortion always drops, but using the elbow and the distance to the line, the clusters, sorry, and the distance to the line, we can calculate its score, which you see in the top right. And this score will have been the least out of all of these, or at least it'll have the least increase as k increases. So k-means does assume that clusters are round, which obviously isn't the best for something as varied as population variables. There are some people that could be poorly housed but doing very well, and vice versa. People who've lost a job, for example. But regardless, it is useful for general data so that we can uplift averages within a profile. So this is the payoff of the whole project. Numbers alone don't really mean anything, but here we have our cluster data. So I compared the average on each variable against the 25th and 75th percentile once I had my final results in order to determine what parts of a profile gave it its characteristics. So you'll see that more in the Google Colab sheet. But I flagged the variables as strong or vulnerable and gave a label column as well so that that could be pulled whole part for analysis later. And I've produced this color-coded graph with the 3 profiles, with one mixed, one above average, and one below average on the community well-being index. So for the planning implications, if 2 communities share a similar overall community well-being score, but one has strong income, for example, and the other is average, they have different interventions. Pouring resources into income support for the first community would miss the problem. So the core argument is that a single combining index is inefficient for ranking, really. The data at the heart of these indices is what is more useful, and publicizing and making that useful to these communities is the priority. The combined index is the wrong tool for deciding what to do about the fact that the index is low, which is counterintuitive. This kind of indicator level clustering gives planners something the score can't, which is an indicator of what needs to be done. So that's everything for my presentation. But I have links and everything to my work here. So for my exploratory data analysis, you can see that I started by generating that first graph we saw, which has the histograms for all 3, we don't know about the clusters yet, but it has the histograms for the whole plot. This is income against income, so you can see the distribution of income in the set. And then we have all of the input variables plot against each other in the remainder of these graphs. The correlation heat map was the most useful thing by far. I think the most interesting part was that labor force activity isn't as strong of a predictor as income, which should be obvious since there's other ways to make income than labor, but it's interesting to see it in data. In the box plots here, you can see with our relatively small data set, the indigenous communities in Canada on the CWB are relatively clustered with very few outliers. The full data set was much more skewed. But yeah, that indicates to me that we're probably missing a number of outliers that are indigenous communities and minorities that live within larger non-indigenous communities. But that's a weakness within the data set we're working with, the CWB. Nothing we can do about it. So here's the standard scaler being applied, standardizing the data, which we will undo at the end to analyze. And then we have the k-means clustering. So I used the Yellowbrick module, which is an extension on scikit's k-means clustering. So Yellowbrick uses a visualizer and the distance minimizing model from the mean line to get a score for each point in a given range, which I chose arbitrarily as 1 to 15. And it found that there was the largest increase and largest slope, rather, at this point 3. So that's what I went with. And when testing the data, I did test 2 and 3 to see if it was useful to have that moderate. And without having an average, it does just split it into 2 groups, where one is lower on everything and one is higher on everything, which isn't as useful as what we wind up getting. Here we have our centroid definition and clustering. So from our text data here, I'll explain what I did for my clusters. So cluster 0 represents our average or our median cluster. It has, these are its median data points with 61 on the CWB. And I've also defined the standard deviation and the mean, as well as the first and third quartiles in order to interpret these. So if a data point is outside or below the 25% quartile, it's labeled as vulnerable in the descriptions and underlined when it's printed using our formatting function. And when it is above the 75% quartile, it's bolded and listed as strong in our description. The formatter has a limit. It doesn't choose every label that's given. It uses a second check of the standard deviation. So the data is only considered significant enough to be formatted if it is outside of one standard deviation of the mean. So in this case, we see the average is truly average. The vulnerable cluster doesn't have any specific point where it falters, although on education it comes very close, income as well, to being more than one standard deviation away from the mean. The strong cluster is the most illuminating for our data set, in my opinion, where you see that the CWB is strong outside one standard deviation, and the most statistically significant indicators of that are education and housing, which in correlation with our heat map graph, which corroborates our correlation heat map graph. So you can see our final weighted cluster score, which is the same as what KLVO predicted, or at least very close. We have the number of observations in each cluster. It's fairly even, but the strong cluster is the smallest, which is what you expect from a kind of well-being indicator like this. And yeah, each of the cluster descriptions contains the full label, so you can see that income was still vulnerable, and I print these out here just for clarity. Income is still vulnerable. It is in the lower 25% quartile for the first cluster, but it is within the standard deviation of the mean. So it's considered less statistically significant. We could modify this to show everything, but I felt that would get a little bit cluttered. And here you see our final production, which is the original pairwise scatter plot with the histograms, but labeled by cluster. So the histograms overlaid on each other, with the legend here showing the yellow cluster as strong, the gray cluster as vulnerable, and the blue cluster as moderate. So this will be income on income. You can see the vulnerable cluster has the lowest average, which is expected. And you can see the impact that each input variable has on each other variable. Interestingly, the education and labor force activity was very scattered, which shows how, having higher education doesn't necessarily indicate more activity, but we do see a high correlation to income. But yeah, that is everything that I've produced. So thank you very much for listening to my project. Yeah, I'm looking forward to submitting the research paper. Thank you very much.